Well, before we get this one, Luke, you better open up your lightsaber. Okay, I think we're ready now. So, how would we solve the non-homogeneous system x prime equals matrix A, which is 0, 2, negative 1, 3, times matrix X, plus this vector F, 2 in the top and e to the negative 3t below? So, I guess the first thing to do is find eigenvalues and eigenvectors for our matrix A, because that's how we're going to find our fundamental matrix. We're going to pretend this isn't here, so we can find the solution of the homogeneous system. And 0 minus lambda, 2, negative 1, 3 minus lambda, find the determinant of that matrix. Well, that turns out to be, look, lambda squared minus 3 lambda plus 2, and that's kind of nice because it has eigenvalues just 1 and 2, right? They're the solutions for this. For 1, we examine the augmented matrix, negative 1, 2, and negative 1, 2. Well, isn't that going to turn out nice? Just add, or do this row operation, multiply the top equation by negative 1, and then add the 2, so we wind up with all zeros in the bottom, so k2 is arbitrary, k1 minus 2k2 equals 0, so k1 equals 2k2, and the eigenvector is k times 2 in the top, 1 in the bottom, or any multiple of that, times our constant k2, which is irrelevant because it's an arbitrary constant. So, for eigenvalue lambda equals 2, we got 0 minus 2, 2, and 1, negative 1 rather, and 3 minus 2 would be 1. So, we start off with this. Let's make it nice. Negative a half times row 1 puts a 1, 1, 0, or 1, negative 1, 0, and when we just add them together, this is never got easier than this. 1, negative 1, 0, and k2 is arbitrary, so looks like the top one says k1 minus k2 equals 0, so our vector associated with this eigenvalue is 1, 1. So good, and that means we've got our solution, right? Our xc is c1 times e to the 1 times t times its eigenvector 2, 1, and c2 times e to the 2 times t times its eigenvector 1, 1. And we could write that, if we wanted to, as 2 e to the t plus, 2 e to the, let's try to say this better. If I wrote this all out, I'd get, in the top, I'd get c1, 2c1 e to the t plus c2 e to the 2t, and then in the bottom I would get c1 e to the t plus c2 e to the t, but that would happen to be 2 e to the t square matrix, and up in the upper left, and then e to the 2t in the upper right, and 1 e to the t in the lower left, and 1 e to the 2t in the lower right, times our vector of constant c1, c2. So this is our fundamental matrix. So now the tough part is, how do we find the inverse of that fundamental matrix, because we're going to need that. And so we start using the Gauss-Jordan elimination method, where we write our matrix next to a 2 by 2 identity matrix, 1s on the diagonal, 0s elsewhere, and then we perform row operations on this part until this is an identity matrix, and then the inverse matrix will be over here. So the first row op, we want this item to be 1, so we multiply the top row by 1 over 2 e to the t, and that gives us our 1. This would be 1/2 e to the 1t now, see, because we divided by e to the t. And then this is going to be 1/2 e to the negative t, because we divided by this. And of course 0 here, because that doesn't change. And then what? Then what we should do is negative e to the t times the first row added to the second row, and that gets us a 0 here. See, negative et times row 1 plus row 2. So row 1, of course, will remain unchanged. Negative et times e to the t times this added to this makes this a 0. Negative e to the t times this added to this, negative e to the t times this added to this gives us a 1/2 e to the 2t negative a half e to the 2t. Remember, we're multiplied by negative 1 e to the t. So negative a half plus 1 is positive a half e to the 2t. Now, continuing, multiplying by e to the negative e to the t, this just becomes negative a half. Add to this makes this negative a half. And then negative e to the t times this add to 1 is just still 1. So we're not there yet, but it wouldn't be hard to make this into a 1 by multiplying by 2 to make this go away, and e to the negative 2t to make this go away. So that yields for us the 1 here that we wanted. Negative 2 e to the negative 2t times this is our 1. Negative 2 e to the negative 2t, well, sorry, that's 2 e to the negative 2t times this is going to be negative, the 2's cancel, so negative e to the negative 2t. And 2 times e to the negative 2t times this is just going to be 2 times e to the negative 2t. And now we're almost there. All we've got to do is make this a 0. And so negative a half times e to the t times the second row added to the first. So we'll do that very thing. So let's see. Negative 2 negative a half e to the t times this add to this still gives us a 1 here. Negative a half times e to the t times this added to this is going to make a nice 0 here. That's what we wanted. Now it gets dicier. Negative times a negative is a positive, so we multiply by this, we're going to get positive half e to the negative t, and we're going to add that to the half e to the negative t we got there now, and then we'll get 1 e to the negative t. So let's keep going. We've got one more of these to do. We got to multiply this item by negative a half e to the t, so negative a half e to the t, the e to the t and e to the negative 2t gives us e to the negative t. And the negative a half times 2 gives us negative 1, so we get negative e to the negative t up in the northeast corner. And so there is our inverse matrix. If we wanted to verify, we could check that that inverse matrix times our fundamental matrix is a 2 by 2 identity matrix, and I did check it. You don't need to see that, but I did check it. And it is 1. I didn't want to lead you astray, so I checked it with my software. But it does come out to be a 2 by 2 identity matrix. Okay, next we need to find phi inverse times f. Here's our phi inverse. Here's our f. And so multiplying that, we get this times 2 plus this times e to the negative 3t. Well, that's 2 e to the negative t, and then minus e to the negative 4t, because e to the negative t times e to the negative 3t, add the exponents e to the negative 4t, and a negative times a positive is that negative. So then that's the top row. We get the bottom row by multiplying negative e to the negative 2t times 2, there's that, and then 2 e to the negative 2t times e to the negative 3t, so that comes out to be positive 2 e to the negative 5t. And then we need to integrate this. And integrating 2 e to the negative t is just negative 2 e to the negative t. Integrating negative e to the negative 4t, we get positive e to the negative 4t over 4. And integrating this, the 2's cancel and the negatives cancel, so we wind up with just e to the negative 2t, and then integrating this one we get negative 2/5 e to the negative 5t. That is our phi times f of t, but that's not xp yet. We have to take that integral and multiply it by our fundamental matrix. So here's the fundamental matrix times this result, and let's see what that turns out to be. 2 e to the t times negative 2 e to the negative t plus e to the negative 4t over 4 is, well, this times this is negative 4. This times this is 1/2 e to the negative 3t, and then plus this times this which is 1, because e to the 2t times e to the negative 2t is e to the 0, which is 1. And then this times this is going to give us an e to the negative 3t, negative 2/5 e to the negative 3t. So I think you can see where all that came from. And I can simplify it a little bit. So here it is, simplified. It's really just what's 1/2 minus 2/5? That's 5/10 minus 4/10. So 1/10 e to the negative 3t, and then minus 3, and then negative 2 plus 1 is negative 1, and 1/4 e to the negative 3t minus 2/5 e to the negative 3t. That's, I guess I'm going to have to go to 20ths. 5/20 minus 8/20 is negative 3/20 e to the negative 3t. So, wow, it doesn't take many of these to make a dozen. So our solution is our fundamental matrix times a vector of constants plus this thing that we just found. This is our xp right here. This is the xp.